module will include a definition of the open-close principle. We'll look at the problem that the principle represents and solves. We'll see an example of what happens when one does not follow the open-close principle, and then we'll examine what's wrong with that example, and finally we'll refactor in order to apply the open-close principle to that example. Finally, we'll have a quick summary and we'll look at some related fundamentals. The open-close principle states that software entities such as classes, modules, functions, etc. should be open for extension, but closed for modification. This specific example is from Wikipedia. This slide demonstrates how the open-close principle can apply in a graphic notation. It says here below, open chest surgery is not needed when putting on a coat. Likewise, when you extend your software, you should not need to go and dig around in its internals just to change its behavior. You should be able to extend it by adding to it new functionality and new classes and functions without the need to change your existing classes and functions while still achieving behavior. So the open-close principle offers up this sort of conundrum in that it's stating that things should be open to extension. New behavior, changes behavior can be done in the future, but yet close to modification. What does that mean? That means you shouldn't need to change the source code or the binary code. You shouldn't have to recompile the existing pieces of your application necessarily in order to achieve this. Dr. Bertrand Meyer originated the term open-close principle in his 1988 book, Object-Oriented Software Construction. So how do we do this? How do we change behavior without changing code? The key is to rely on abstractions. Once we start to rely on abstractions in our code, there's no limit to the number of different ways we can implement that abstraction, and thus no limit to the number of ways we can change the behavior of the code that's using these abstractions. So what do we mean by abstractions? Well, in .NET, abstractions include interfaces as well as abstract base classes. In procedural code, we can also achieve some level of the open-close principle using parameters. Let's look at an example of the code that's been written in such a way that it is not closed to modification, nor is it open to extension without having to hack at the actual source code. Let's look at this example here. We're a commerce solution that includes a cart, for instance, for a shopping cart. The shopping cart has a list of items. Each item is of type order item. If we look at order item, we'll see that it simply represents an item that one might place in the cart, which has a quantity and a stock unit or SKU associated with it. The cart has this important method called total amount that is used to determine what the total price of all the items in the cart should be. And because this is a pricing calculator example, you can imagine that there are different types of rules that determine how various order items within that cart are totaled up to reach their final total amount that the cart represents. In order to make this easy for a demo, we've stated that the SKU is what determines the rule. And so if the SKU starts with the word each, then that item is going to be exactly $5 times the quantity. So we see the rule simply order item quantity times 5. However, if it is rather the weight, then we're going to take the price as a unit price per kilogram. And so we'll take the order item quantity, which we decided for some reason in grams, and we're going to say that it's $4 per kilogram. Finally, we have this concept of special as a third rule for the SKU. Special items only cost 40 cents a piece. However, they have 3 for $1. So what that means is if you buy one, it's 40 cents. You buy two, it's 80 cents. You buy three, it's $1. And the way this has been implemented is to simply provide a discount of 20 cents for each set of 3 that comes along. Now you can imagine that these rules have been come up with by the business user, the owner, whoever it is that is trying to maximize the sales of this particular store. And we know at this point that there are more rules coming. So this is a valid time for us to be looking at this and thinking, how can we change this code in such a way that we don't have to go and edit this particular method every time someone comes up with a different way to price the items that are in the cart. Now it's important too, before we make any changes to this sort of code, that we look at some of the tests that are applied to it. And of course, before we do any refactoring, ideally we would have tests that represent the current state of this code. And so we have over here a unit test class that we can run that will verify that this is doing what we expect. So let's go ahead and run the test, and we'll see that they all pass. And so this is telling us that the cart total should return 80 cents with 2 special items, 2 with a half a kilo weight item, $2 with 6 special items, 5 with 1 each item, and 0 with empty, and all of these pass. And if you look through each one of these tests, you'll see that they're very straightforward. We have a cart that's set up at the class level and is new up before each test in our setup method. And then our first method simply says that our cart is 0 when it's empty. So when it first starts, we haven't added anything to it, and we assert that it has a value of 0. If we added each widget with a quantity of 1, we expect it to cost a total of 5. If we add some peanuts that are valued by weight with 500 grams, we expect that it's going to be 4 times half a kilo is 2, so we end up with $2. We expect 80 cents if we buy 2 of the special candy bars, and that's what we get here. And we expect it to be, with a total of 6 of them, that's 3 for $1, 2 for $1 makes $2, so we expect to get $2 in that case. Now, think about how we would add additional rules to our cart for additional items here, where, for instance, maybe it's buy 4 get 1 free or something like that. Now we have to add yet another else if to our block here in order to achieve that kind of a rule. And very quickly this type of thing gets out of hand. And so we really like to apply the open close principle at this point to make it so our cart is much more flexible and maintainable and does not need to have survey performed on it every time someone comes up with a new pricing rule within our model. So the problem with our cart is that adding the rules requires changes to the calculation method with each new rule. Now every change that we add can introduce additional bugs and requires retesting. Plus we tightly coupled our pricing logic with our cart, so that anytime we want to be able to test the new pricing logic, we have to set up a cart and actually test the cart rather than just testing a pricing rule. Ideally, we want to avoid introducing changes that cause cascades through many different modules in our application. And in this case, if there were many different things depending on how the cart's behavior worked, then each change to the pricing within that cart could potentially cause this sort of change throughout our application. In your own applications, you're going to want to look for things that tend to be tightly coupled in many different parts of your app, and ideally want to remove those dependencies by introducing abstractions that can separate those from different areas of the application. This is something that's called introducing seams within your app, where you can separate different parts of your application from one another. Ideally, when we're adding to our software, if it's complying to the open-close principle, the way that we'll be introducing new behavior is through the writing of new classes. And you'll find that if you follow the open-close principle, oftentimes when you're adding additional behavior or changing the way your software works, you're doing so by adding multiple new classes. And as a consequence, you'll typically have smaller classes. Each one is doing a very tight focused job and following the single responsibility principle as well. The benefit of adding new classes in terms of how easy that code is to write and to design and to test is that by definition nothing depends on these new classes yet. They didn't exist previously in the application, so none of the code that's already there knows about these classes and can have some dependency on it that you'll be breaking, perhaps inadvertently, when you change that code. Also, new classes don't have any baggage that your existing app may already have in terms of dependencies on infrastructure or other hard-to-test classes. So you'll be able to start fresh with this new class and make something that's very straightforward, simple, easy to design, and hopefully easy for you to test. Now, there are typically three approaches to achieving the open-close principle that I've found in my experience. The first one is really more of something that you would be able to do in a procedural programming language, and that is to use parameters. And so by exposing parameters in your application or in your class or in your function, you allow the client to control behavior via the specifics of that parameter. Now, this typically involves sending some kind of state to a function or to a class. For instance, a string that has some information in it, and based on that information, your class will behave a certain way. But realize, too, that you can combine this approach with delegates and lambda expressions so that it can be very powerful at actually changing exactly how the class or the function behaves and what it actually does. An example of how you can use parameters to achieve the open-close principle that I like to tell is imagine that you have a digital camera and you've written a C# program that pulls all the files off of your digital camera and drops them into a folder on your C drive. You've decided, or I've decided, my name is Steve, that I'm going to put all these files into a folder called Steve's Pictures. And I decided to just hardcode that into my C# program. Now, the program works so well that I decided to post it up on my blog, and a lot of people start to use it, but I soon started getting complaints that the pictures all end up in a folder called Steve's Pictures, and not in some folder that they might prefer them to be in, especially those people out there that aren't named Steve. Now, the easiest way for me to change my software and allow it to go to whatever folder the user wants to specify is to introduce a command line parameter where they specify the output folder for this program. If I don't do that, then the only people that will be able to use my software in a way that they would like to use are developers who are going to have to open up that code, change the string where I set the full name, rebuild my application, and then run their application such that it goes to whatever folder they've set. Now, if they're smart, they'll introduce a parameter. But if they don't, and there's a guy named Bob that wants to have his pictures in Bob's Pictures, he could in fact just go in, change that one line in my C# file, rebuild it, and now he's got a perfectly usable program that always drops the pictures into Bob's Pictures, and he's happy. However, the fact that he had to change the source code means that that was not, in fact, following the open-close principle. Now, the second way that we typically want to approach the open-close principle in an object-oriented programming language is to use inheritance, and specifically a pattern called the template method pattern. And we'll talk more about the template method pattern in other videos, but suffice to say that this is a pattern by which you can create the default behavior in a root path. Oftentimes you'll create a series of steps that need to be followed in a particular order, and then within your child types, you can override what each one of these steps might do by overriding that template method. The third approach, which is the one that we're going to look at now, involves composition in addition to inheritance, and it uses a design pattern called the strategy pattern. With the strategy pattern, the client code, the code that's calling the behavior, depends on an abstraction. And this provides a sort of plug-in model where the actual work that's being done is defined in a class that gets injected into the actual class doing the work. So with this particular approach, we have the implementation utilizing inheritance because it inherits from a base class or an interface, and the client utilizes composition because rather than using inheritance itself to achieve this new behavior, it exposes a way for other classes to pass into it an implementation which it then sets on a field in its class. So now let's look at how we can refactor our pricing calculator in that shopping cart so that it has a better design and maybe conforms to the open-close principle a little bit better. Let's have a look at how we can refactor our shopping cart so that it takes advantage of the open-close principle. The first thing we need to do is identify the fact that there is some other job that this cart is doing, and that job is pricing calculation. So we need to define an interface that defines what is that pricing calculation? What does it need to do and how should it behave? So what I've done is I've created an iPricing calculator interface that simply is able to calculate the price for a given order item. With this in place now, we can go back to our cart, look at its total amount, and see